So if we're talking about chapter 11, we're moving into geometry. So we need to think about the figures. 11.1 is a really straightforward chapter or section that just requires you to understand the basic figures and some angle measurements. So we're going to talk about that right now. Okay, sorry, I didn't realize it was recording. Okay, so one other thing that I want to mention is this history that geometry has. Before a Greek philosopher named Euclid, we really were not analyzing the figures. We were dealing with physical calculations to help us do things in the world that you would imagine, like building things or measuring to make spaces or to calculate costs of stuff. But Euclid really wanted to figure out what was true about each shape that we're working with. What do we know and where can we go from there? So the way that all geometry is taught now goes based on his progress. So he wrote a book called Elements, or at least his school of students and him wrote a book called Elements that first of all defined the figures and then started with the most basic truths they knew about the figures and then used those truths and a set of rules, which we're not really going to get into the rules too much, but they used those rules to then progress to new things that they found were true. And so that is how we teach basically all math, but that's definitely how we teach geometry. We say, what are the pieces? What do we know about them? And how can we use what we know to find new information? It is actually not the way geometry works in our world in a lot of places. He worked with straight lines. And it turns out that we live on a round planet. So a lot of his straight line geometry doesn't actually work when we're talking about bodies in space. But it is typically the case and what is true when we're working in our day-to-day lives. So that's where we begin. Okay, I want you guys to consider, how would you define the figure that is on this screen right now? How would you define a point? What would you call it? What definition would you use, and what would you use to prove characteristics about it? Because in my mind, and what we have learned, is that a point is the most basic figure in our entire world. It makes up everything else. So how do you define the fundamental building block of everything else? Really, mathematicians don't. This is an undefined term for us. It's something that we assume, okay? And we assume this along with two other figures. So I'm going to include another piece over here. Oh, that's not a good dot. Come on. There we go. So I'm going to include this piece over here. That's just another point that I've got. And consider what that will make. Now, I hope you were able to guess that you can make a line from 2 points. You just simply connect them with all the other points between them. But notice that my line that I have in the position of the 2 points we created actually continues on past those 2 points. Because what happens is you see this arrangement of points in between these two right here, this one and this one. We'll talk about how I'm referring to them in just a second. But all the points in between are, those are filling in the spaces. But who's to say that we're not talking about all the points continued in one direction or the other? A line is not actually what you and I draw when we're talking about lines in class. If I say that I'm drawing a line and it does not look like what you see here, it is not a line. It's actually a line segment. We'll get to that in a minute. But basically, a line continues. So let me make sure I write this down. It continues in either direction, in both directions. Infinitely. That's something to note about this here. And something else to note is that there's no other way to connect those 2 points. Oh, that was an ugly S. So what I'm saying is the line that is highlighted cannot be drawn a different way between those 2 points, because what you will have if you try that, a second, will look like this, or maybe like this, or possibly like this. Not possible, doesn't work. Okay, so in the geometry of that mathematician, that philosopher that I mentioned before, Euclid, you can only connect these 2 points in one way, and that is this unique line between them. And I want you to note that I have another line on the page because I want you to see what it would look like if you don't have the points defined. Now, I keep saying just those 2 points. That's not a very good way of talking about this. If we're thinking about people as points, I'm not going to point to any of you in the classroom and say, oh, that one right there, or that guy right there, or whatever. I'm going to use your name. I use your name from the very beginning as much as possible, and it's the respectful way of talking about things. And I'm not just going to say point either, because that's like me pointing to you, or me gesturing to somebody and saying student there. That's no better than saying that's too generic. I'm not using your name. I'm calling you what you are, which is in the classroom a student. So I need to name whatever points I have. And the way we do that is with capital letters. We typically start with A and move forward. Using X, Y, and Z, not our standard. Those are usually algebra variables, but you can do it. And if I call this point right here A, I cannot call any other point A. Okay, not on this page. I can do it on another problem or another page, but on this page with this problem, that point, that name has already taken. Okay, it's kind of like if I have 3 Stevens in a class, I'm going to try and find some separate, unique identifier. So in fact, sometimes in the problem, you'll see something like that. These little apostrophes. That's like me saying Stephen J for Stephen Johnson, or Stephen D for Stephen Davidson. A and D, or J, Stephen J and Stephen D, that's the same thing as having this A with the little apostrophe or A with the double apostrophes. The way you read that, by the way, is A prime. Anyway, I'm going on forever. Don't worry, I'm not going to take this much time with all of the characteristics. So if you have a line like the one that's also drawn on the page that does not have any letters, you can also, or points, you can also name it using cursive letter, lowercase. So I can name this line L. That's the most common that we'll go with. M. These are the names to start off with. That's an N. You'll see your textbook do this all the time. All right, let's move on. Okay, before we said we had 1 point. Then we named that, okay? Then we had 2 points, and we were able to connect that to make a line. But when you have 3 points that cannot all sit on the same line, that creates a figure. Because imagine 3 points in a room and trying to connect those. So if I toss a penny, a dime, and a nickel on the floor, just not in a straight line, and I wanted to connect them, I would, let's see, let me do this with just some, with my highlighter. I'm trying to connect this here and trying to connect this piece here. It doesn't exactly work because, first of all, I missed the line. Because what happens is that I have to connect them in more than one way. So trying to make that connection, trying to find the figure that is formed, you should see it forming already. It is something flat. And it has shape. It has more than one direction. It goes left to right, and it goes up and down. This is a plane, okay? And this connection I've made, just like the lines before, it doesn't just stop between the 3 points. The line could go in any direction, in both directions. A plane, or what this figure that I'm working here, I just gave it away. This figure that I'm working with here can go in any of the directions as well. So I can just continue extending these lines here until suddenly it looks like this. Now I don't want you to misunderstand me. When I say that you put 3 coins on the floor and try and connect them, it's not that we're ignoring triangles, because that connection could be a triangle. But basically the figure that they make, if you're trying to connect them in a unique way like this, they make a plane, okay? And that plane that's created between those 3 points, just like the lines before. So if you had that line that looked like this, and you couldn't possibly connect it in more than one way, there's no other way to connect. I'm not gonna be able to erase that. There's no other way to connect these 3 points, or to define this plane that I just shaded in without those 3 points included. This is a tough thing for people to understand. Planes can be something, deceptively complex, because you have to try and visualize this as a 3D figure, usually just like what I'm doing here, drawn on paper instead. It's great to be able to discuss this in the classroom because you can point to things, but so you guys are going to have to use your imaginations a little bit. I've got a box to try and help us out. So I have highlighted one side of this figure, and this figure can be determined, so if I pick 3 of these points, they will always be on one plane together. These specific 3 points. Let's call them A, B, and C. So I'm highlighted the plane that they're on together, and I'm actually going to extend that plane so that you can see that it actually that it continues on forever. Whoops. That it continues on forever in that exact plane, in that flat surface. And I'm going to extend it kind of ugly, using these little dashes so that you can see it's not like I'm shading in the box. I'm just shading in that piece of paper, that floor that is covered here. It extends out, so this will continue this way. All of these little lines will continue flat. It's as if that floor just gets bigger and bigger. And again, that's a hard concept to try and teach students. Kids can get that lines will continue on forever, but trying to get that a whole piece of paper can be stretched out infinitely, it's a tough one. you're going to have to try and connect that to that for them in some way. And again, if I were in person with you, that'd be one thing. But even if I weren't, because I teach this online too, all my online students, hello, it's something that you're going to have to think through. And I can't be the one to show you how to think in 3D or how to think about infinity. Okay, last comment on plane ideas. I wanted to show you guys the plane that's connected by the points A, B, and D. So that would be this side right here of this box, okay? Remember that before we had this side of the box down here that we were talking about. I've erased point C so that we're not looking at that as well. So this side, I can extend these lines. And I'm trying not to shade through the box so that you can see that it doesn't go, that it's not part of that gray shaded area. Okay, and then just would continue out through here. Okay, so, and that would just continue on in all 4 directions. Notice that I'm saying all 4. You know, with the line, you're moving in 2 directions, side to side, whatever angle the line is at. But for a plane, you're moving up, down, left, and right every single time, no matter where your 3 points are. Notice again that we had the points right here, and right here, D, A, and B. Before, our point was at C. It's not what we're working with now. Okay, moving on. Okay, let's talk about some terms here. So we're going to talk about coplanar first. If you look at this figure here, you can see that G, F, and H are coplanar. They're on the plane alpha. That's what the little fish sign is, and J is not on that plane. It's indicated because it's not on the shaded area, and I'll show you another way that we really show that it's not there. All right, next we're talking about skew lines. If you'll notice, line GF and line JH, they do not intersect with each other. JH, imagine it's sticking out of a piece of paper, and GF is drawn on that piece of paper. So it's not like it's even in those 2 don't actually hit each other. Again, this line right here, it's sticking out of the paper. And this line right here is drawn on the paper. Okay, and since point H over here is separated, it's never going to touch these lines over here, and point J, it's not going to somehow jump onto the plane so that it can possibly intersect. So they are non-coplanar, and they don't intersect. That's what makes skew lines. Now, I realize I skipped something. I didn't talk to you guys about how to write down lines. So a point, you'll name it using one letter, one capital letter. A line is made from 2 points. So you need to name it using 2 points. So in this case, I named on both sides. Okay, then I can actually rewrite this as G if I'd like. If you don't include the label on the top, you are not talking about a line. Sometimes I don't know what you're talking about. You gotta name it properly. If I am expected to say your name, then you're expected to write down this point's name or this line's name. Next term, concurrent lines. I gave you GF and FG, so let me highlight those. Here is GF. I started on the side of G and I went towards the direction of F. Next, I start with F because in the next line is named FG, and I go in the direction of G. those are the same line, so they are concurrent. I can actually find more concurrent lines because I added another point in here. So GK, KF, all of those are concurrent with each other, and there's more combinations that can be made depending on the amount of points you've got. Next up, we have parallel lines and perpendicular lines. We all know what these are, but I want to note how you can show in pictures and in symbols, how you can write out the relationship. So, parallel lines, you've got them drawn here. I've got line L and line M. I want to show that these two are parallel. I can write a little symbol on the picture, 2 little arrows, one on each line, and that'll show that they are actually parallel to each other. So in fact, if I added another line over here, and you're not sure, you're like, are those parallel? And you see this, that means that all 3 of these lines are parallel to each other. So the way you write this out, line L, line M, and then you do a double bar. L is parallel to M. That's what you're looking at there. Okay, perpendicular lines, you see the 2 different versions, the ways that you might see it. The way that you would draw this out is you draw a little box, a little angle there. It shows that perpendicular lines have right angles to each other. Okay, and the way that you'll write this out, so for the first picture we have line, I'm going to call this line AC, is the horizontal one. I'm going to do my little line symbol on top, is perpendicular, so you're going to actually draw the figure. Draw a line perpendicular to line BD. And we haven't actually talked about the figure that you're looking at in BD, but it's a point on one end and an arrow on the other. So that's what that symbol top would look like. It's called a ray, just FYI. Then the next one is line N, perpendicular to line P. Next figure, you have an end point that connects to another point that continues on forever. This is called a ray. Okay? Connect two rays with one end point and you get an angle with 2 sides and the interior, the space in between. And as your 2 rays continue on forever, this interior continues on forever. It's not like you can find the area of it or something like that. When they share an endpoint, that is called a vertex. It's very, very important to know the vertex of an angle. It's important because just like before, we need to be able to name our angles. That vertex will always be the center of the name because it's the center of your angle. So for this one here, I can name this angle A, B, C. I need 3 letters because I'm talking about side, vertex, side. Or, in this case, I don't have any other angles, so I can name this angle A. Okay, or I could go in either direction. I could also name this angle CBA. The big thing is I named that angle A. That is wrong. That's angle B. Sorry, guys. The big thing is that B is the center of each of these names. Now, just like before, I need a symbol to note it off or to mark it down. So the symbol will be the shape of an angle. It's very straightforward. We've got 4 types of angles that we want to, or 4 different general categories. We've got our cutie little acute angle. It is less than 90 degrees. We should remember this. Then we've got our right angle that we mentioned before. It is 90 degrees exactly. Then we have our obtuse angle, greater than 90 degrees, but less than 180. And then finally we have our straight angle that is equal to 180 degrees. We can, of course, have angles bigger than this, but these are the categories that we talk about. Note that the way that these angles work, this whole time I've had acute written down, so sorry. The way that these angles work is talking about the width based on the rotation size. Okay, rotation is a big part of angles. So you need to know these measurements, these categories. Last thing I want to talk about is the topic of circles. We're just going to go through the parts. There's a lot of different characteristics and properties, a lot of theorems that could go along with this content, but we're almost up to 30 minutes, and this is a lot of information that I've jammed in here, a lot of just procedural stuff. So we're going to move forward. You don't need to worry too much about individual content for these topics, or for these pieces. Number one thing that people know about a circle is that it has a center. Typically, it's going to be the letter O, but you can name it just like any other point. And then the next piece that people know best is the radius. Of course, a radius has two endpoints because it's a segment. It's a line segment. It has the endpoint at the center of any circle and at the perimeter, basically, the circumference of the circle. It ends on the actual circle. My picture doesn't look very, there we go. Now, if a radius is on a straight line, like you see here, then you can actually extend the radius to the opposite side of the circle to make the next most, I'd say famous or most well-known part of a circle, the diameter. Diameters are line segments that have two endpoints on the circle, and they go through the center of the circle. That's probably the most crucial part of a diameter, but you need all three bits of that. Now, so a diameter has two defining characteristics of it. But let's say we took away one of those characteristics. Let's say we did not have the center as part of our segment. That means that our line would look like this segment here. This segment has both endpoints on the circle, which is important, but it does not run through the center. And in fact, I could draw segments that look like this all over my circle. Both endpoints running and through more than one bit here, but both endpoints are running through the circle, but not through the center. Again, these are called these are called chords, okay? And no matter whether or not your chord runs through the center or not, it actually creates another piece of the puzzle for us, or piece of the pie, called an arc. Now, I've got two chords here. I've got a diameter and I've got just a regular non-special chord. And I'm going to show you what an arc will look like. This guy right here. Now, if I go to the diameter and I want to highlight an arc, it's going to be a little bit tougher. Hopefully you're seeing why. Because I can go in this direction, or I can go in this direction. I'm just going to scoop around here, still talking about that piece. Either one of those are possible arcs created by the diameter. So when you're naming them, the name is important. It's important that it has the endpoints and whatever point that one more point that it runs through. So this would be called arc A, C, B. You can do a curve over it. If I wanted to do an arc from this side, I'd call that A, D, B with an arc over it. And for smaller arcs, well, so let's yeah. Okay, so sorry, I don't remember what I said before I paused the video, but basically this little chord that we've got drawn here, ignore the diameter right now, creates a minor arc, which is less than half the circle, and a major arc, which is more than half of the circle. So you might wonder, what do we call an arc that is half the circle? You'd call that a semicircle or a semicircle because it is half. Okay, semi is a prefix for that. So these are the different types of arcs that you could possibly have. Very last topic we want to cover, almost exactly at 30 seconds, is central angles. We have the central angle drawn here of AOC for the arc AC, okay? And I'm just going to highlight what that central angle would look like. It runs through the center of the circle. And let's say that arc AC had an arc measure. So measure of arc AC is 36 degrees. That means that the measure of angle AOC is also 36 degrees. And vice versa. Let's say that the measure of angle AOC is, we'll say 42 degrees. That means that the measure of the arc is also 42 degrees. Okay, there's a lot of different little topics that I tossed at you. Chapter 11 is just a bunch of little topics. We've gone through the big theoretical stuff, and now we're just working with individual parts of geometry for the rest of the semester. Hopefully this gives you a good foundation to move forward.